Hi guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to continue our discussion about machine learning review and actually explain some stuff that we will use a lot in deep learning. So we discussed to the choice of cost function is one step in machine learning algorithms to design them. So for the regression task, we saw that mean squared error is a suitable loss for regression, but for classification, we learned that it is not a suitable loss function. So we have other loss functions to do the classification. We have seen the SVM and how to design SVM and how SVM works. We could actually write the loss function of SVM as it's right down in here. We actually talked about it, how to design an SVM or support vector machine. So it's called actually SVM loss or hinge loss. It is commonly used. Maybe it is more common than SVM loss in deep learning terminology. So as you could see in here, we have a maximum. So this is the first term, and it could kind of act like the regularization term. In here we have we are getting some kind of score for the input xn. So in other words, we want to know that whether for input x, so let's say we have 0, the labels are -1 and 1. So for +1 class or for 1 class, we want the prediction value have the score greater than 1 from the -1 class. So we want to have some kind of margin. We actually saw in the SVM itself that we want to have some kind of margin to separate two classes. So in the next slides we talked about it more, and so this is one kind of loss function for classification. Another thing that we learned is actually logistic regression, which we could write the logistic regression cost function as this loss function, which is kind of cross entropy with the sigmoid activation function. Okay, so this is a logistic regression and this is SVM for these two are used for classification. So for classification, when we have multiple class, we could think of multiple class that we have different decision classes. So let's say we have this class, and this class. So we could think of, we have F1 in here, F2 in here for separating these two classes, and so on. So probably maybe this one to separate other classes. So it is actually one way to design multi-class classifiers, and we could put the parameters of each function, of each decision function, in a matrix to have a weight vector for all of these decision functions. Okay, for example, in multi-class SVM, we could write the loss function as this form. So actually we saw this is hinge loss, so maybe it is a more clear way to write the loss function in this way, and Sj is W transpose X for the input of Xi. So we could think of Sj and Syi as the score of the classes. So it means that we want to, the Syi is the true class, and we want to that the score of this class have a margin of 1 and plus the score of j. So we want to, for a score of yi, we want to have a higher score for the true class. So let's say we want to classify cat, dog, and frog. So we want to, let's say the input is the input image is cat, so the true label is cat. We want to have our algorithm probably gives us 3 score for each class. So we want to the score of the cat class is high, and we want to have this score have a suitable margin from these scores. In other words, we want to have these scores are relatively low in comparison with the score of cat class. And so this is what these ones do in here. Okay, so we could write this the Sj and Syi we have based on W transpose Xi, and so we could think of these as the score of the class J. So this is hinge loss. Now I hope that you grasp kind of intuition about the hinge loss, and this is actually, we know that this is L2 regularization, which is just second norm. In here we use, because we have a matrix which is W, the second norm in matrix, we could say that it is Frobenius norm of the matrix, but it is just the element-wise squared of sum of all elements of the matrix. As an example, we could think of, so let's say we have, this is a digit from MNIST dataset. We will see lots of examples from this dataset later. So it has some digits. They are 28 by 28 images. So we have 28 times 28 pixels, which is 784 pixels. So we could vectorize the input as we did in here to vectorize the image matrix in here. And we have, for the W, we have the W for class 0, W2 which is related to class of digit 1, and so on to W9. So because this data set has 0, 1 to 9 digits, and images could be 0, 1 to 9, so we have 10 classes. So the weights of the of our model matrix has 10 rows in here and 784, which is the dimension of the vector x, columns in here. Okay, and these are just the biases for each class. Okay, so how to calculate them? So let's say we have again cat, car, frog classes, and this is the input image. We just vectorize that image in here, so we have 56 in here, 231, and so on. And for each class we have a row in a weight matrix. So this weights related to cat weights. Okay, and these are related to car, and these are related to frog, and we multiply this matrix by this vector, which is the input vector, and we add the bias term to get the score of each class. Okay, so this is how our classification model works. It gives us the probability of it is not actually probability, it is just some kind of score of each class. Okay, one of the things that we talked about it is actually we could include the bias into the weight matrix if we add just one dimension to x, one extra dimension, and put it as always 1, then we could append or concatenate the bias vector to the weight matrix and see this as just W transpose X. Let's say X tilde. So the new matrix has the bias itself, so we don't need actually to use this notation. So we talked about it before, but just to review, instead of this we could write this in this way. Okay, so this is an example of hinge loss value for some images. So let's say we have cat in here, we have a car and a frog in here, and we trained our model, and we want to know what is the loss function for each of the inputs. So let's say for this input we calculated this value, and we got for cat we got this value, for car 5.1, and for frog minus 1.7. So if we calculate the loss function, the hinge loss for this is 2.9. Just note that when we take this input to the algorithm, we want to have the highest score for the cat, because this is actually a cat, but the algorithm is predicting wrong, and it predicts actually it is a car, but we know that it is a cat, so we have a loss in here. And as you could see in here, we have a loss for this, which is actually a car, misclassified car, but we don't have any loss for frog because it is minus 1.7, and we have 3.2 in here. So we could see that actually this loss is actually a one-sided kind of loss. In other words, because this is less than the cat, we don't need to penalize this, or mathematically you could think you could see that in here the maximum of 0 and minus 3.9 is 0. So okay, and for the car in here, for example, you could see that the score of car is the highest, so, and we have greater than one margin, so we have 4.9 minus 1.3, which is 3.6 margin from the cat score, and we have 2.9 margin from Froggy score. So we are great in this prediction. So we actually should not have any loss. And if you write the loss function, you could see that the loss function is 0. And also for this one, you could do the same thing and calculate the loss function. Now I think you have the intuition about the SVM loss or hinge loss and how does it work. Okay, so until now we saw that actually how to use the SVM loss, but the output of SVM loss is just a score, and we could not actually get a suitable intuition about these numbers. So one way to have the intuition about the numbers is to convert them to some kind of probability. So if the algorithm tells us this image is 90% a frog, 5% car, and 5% a cat, then we have much more sense about these numbers than just these scores, because these are kind of unnormalized scores. So could we convert this one into some kind of probabilities? The answer is yes, actually. We could use multi-nomial logistic regression to do that. So again, we could calculate the score of each input, which is WK transpose X, and we just need to get the exponent of that input and that score and divided it by the sum of exponents of all the scores. So the reason for doing that is actually by exponenting that you are guaranteeing that everything will be positive in here. So all of these are positive, and when you divided it by the sum of all the exponents, it guarantees that sum of all the probabilities will be 1. So the score in here, the sum of all of these should be 1. Okay, so this is one way to do that actually, and there are some other kind of explanation for why we use it, but we don't want to enter in the probability in statistics for now. So we call it softmax function. And it actually could convert the scores or unnormalize the scores into some probabilities. Okay, so the maximum log likelihood, which we have seen in the information theory part of our class, is when you want to maximize the log likelihood, you could think of that as the minimization of negative log likelihood of the correct class. Okay, so the we could write the cross entropy loss as minimizing the negative log likelihood in here, and so this is the negative log likelihood and cross entropy loss. We call it cross entropy loss, and we use that a lot in deep learning. Okay, so let's calculate some of these for an example to get some intuition. So let's say we for this image we calculate W transpose X plus B, and we got these numbers. So the next step is to get exponent of these. So this is A exponent 3.2, we have 5.1 minus 1.7 in here, and then we just divided this one by sum of all of these. So we have 24.5 divided by 24.5 plus 164 plus 0.18. So as you could see in here, now we have we could have probabilities in here. So the sum of all of these is 1, and we could say that the algorithm predicts that the input is 30%, 13% is cat, 87% is car, and 0% is frog. So it actually does not doing very well because it predicts it is actually car. So if we calculate the loss function for the first class, we could see that it is 0.89. Okay, so it will be 0 if it predicts the cat with the score of 1. So you could see that now the cross entropy loss is actually a really powerful loss, because it wants to train the algorithm to somehow convert this into the one probability for the input, not 90%, not 99%. It just wants to penalize the algorithm until it gives the 100% for the cat input. Okay, so we talked about the cross entropy before, so we could write the cross entropy as the minus sum over qx times log of p of x, and we talked about that q is the true distribution and p is the estimated class or estimated model of probabilities. So and because we applied softmax classifier, we have these for p of x, so we could actually calculate the cross entropy loss for the training data. And the true distribution is actually based on 0 and 1, because we have 0 class and 1 class. And we know that the relation between the KL divergence and the cross entropy is actually, we could write the cross entropy as the entropy of Q distribution plus the KL divergence of Q and P. So we have seen that the KL divergence is some kind of distance, but because it is not symmetric, it is not actually a distance, but it is kind of a divergent metric to see how Q and P distribution are different from each other. So we could write the cross entropy as the entropy of the distribution plus the KL divergence. And the loss function when we have the cross entropy loss function, it means that we want to minimize the h of q and p. So it is equivalent to minimizing the KL divergence, or in other words, we want to design a p that is estimating the true distribution. So if you remember that this was our original idea behind the many machine learning algorithms, that we wanted to estimate the true distribution with another distribution. Okay, so as a summary, now we learned the softmax. What is softmax? loss, what is softmax and what is log likelihood, what is negative log likelihood, and how we could apply cross entropy loss. We have seen SVM loss or hinge loss, and the full loss is actually, we have another regularization term in that. So these are the loss per each training data. So when we want to calculate the whole loss for all the training data, we should use this formula, okay? Because for the updating of the parameters, maybe you wonder how to determine these parameters. So for obtaining these, we talked about it, we should use gradient descent method, and for gradient descent method we should calculate the gradient of the loss function in here, okay? So we just calculated all of the training data loss functions, or for a batch of data we will talk about it, and then calculate the loss function for the batch of full training data to update the parameters. Okay, now we know enough about and reviewed enough about machine learning. Now let's jump into some multi-layer perceptron and neural networks more. Okay, now we want to talk about multi-layer networks. So the reason to actually study neural computation is that actually know how the brain works, and the second thing is that actually we could use how the brain works and use the algorithms and the structure of the brain to solve our problem, or the artificial intelligence problem. So we want to maybe some kind of simulate the brain into the artificial intelligence and machine learning area, and so we call them neural networks. This is why they called neural networks, because they are consist of some neurons. So in brain we actually have something called neuron that I'm not very expert in this area, but the general behavior of a neuron is like this. Then for the neuron, each neuron has, let's say this is a neuron, each neuron has some inputs. When the inputs are less than a threshold, we don't have anything as the output. But when the inputs of the neuron pass from a threshold, then we have a spike or an activation or a fire from the neuron. So this was the motivation for creating the neural networks. So the first neural network that created was was binary threshold neurons, and actually the binary threshold neurons was used in them, and it was used by McLeish-Pitts, and they are work without any learning algorithm. So they are work like this. So they are one layer network. So we have some input, then we calculate the sum of W1x, Wixi, then we apply these function, this is a nonlinear function, to calculate the output. So the output could be 0 or 1 because it is a binary threshold neuron. So it is a pretty simple model for for a neuron. So just we calculate the overall input of the neuron, and then we just check that whether it is below a threshold or above a threshold to give 0 or 1. Okay, this is called McLeish-Pitts neural networks. So if this is actually a better figure to figure out how the neural networks work. So we have x1, x2 to xt, which is the total number of features of the input data in here. Then we just calculate, we just multiply each of the inputs with a weight in here, and after that we apply the bias in here. So the theta is a bias in here, and we could have the 0 threshold in here. Maybe you ask why it is not another value, why this is 0 threshold. The reason is that this bias could actually change the way that how this works. In other words, we could think with different values of theta, we could think that we have different thresholds with biases. Okay, so by just introducing a theta in here, we don't need anymore to have a parameter, extra parameter in here. Okay, so we have a threshold unit in this neural network. So as I said, we don't need an extra parameter. So the for a neuron without any bias, we have this activation function. So we could actually introduce an extra variable with input 1 and the weight b. So we could choose the b equal to minus theta to have the 0 activation function, and these are equivalent to each other, so we don't need to have extra parameter theta in here. So this is kind of brain simulation with neural networks. So we have lots of these neurons in our brain, and each of them have some inputs, and again the inputs of these layers, the outputs of these layers are the inputs of the next layers, and so on to get the final output. So for each layer we just calculate the weighted sum of these inputs, then apply the nonlinear function, then again we do the same thing to get the output. Okay, okay, one of the neurons, the special one, is called perceptron. So in perceptron we have something similar to the neuron that we saw. So we have 0 if the wixi is the sum of wixi is greater than theta, or 0 otherwise. Okay, so we want to talk about the perceptron. So in soft perceptron we have the neuron activation function is more smooth than the perceptron. So when we have this function, this is not actually really good, especially in mathematics. Let's say we want to calculate the gradient for this activation function to update the parameters. So we have discontinuity in here, and So it is actually really bad. We have zero gradient in here, and we don't have anything in here. So it is mathematically not a good activation function. So instead of that, we could have the sigmoid. So this is, as you probably know, this is sigmoid, and the behavior of that is something similar to this, but it is a smooth function and the smooth approximation of that. So we call that soft perceptron or logistic, and it's kind of squashing function. It means that we mapped the minus infinity to infinity to between 0 and 1. For this, it is called a squashing function. And so the model of soft perceptron neuron is just the change of activation function. Okay, so now in this case we have real valued output between 0 and 1 for any input, and we have a nice derivative for this function. In each point we have a derivative of the function. We call this sigmoid neurons. Okay, we could actually apply other activations. We will see the activations in the next sessions, but we could apply other activations functions in here. One of them is actually log of 1 plus exponent of x, which is something like this, instead of having, so this is called actually ReLU, or in here we have 0, and in here we have y is equal to x, or it could be expressed as max of 0 and x. Okay, so we called it ReLU. Okay, and also we could have tangent to hyperbolic. So instead of being between 0 and 1, it is between -1 and 1. So if the output classes is 1 and -1, we could use tangent hyperbolic. But if the outputs are 0 and 1, we could use the sigmoid activation function. Okay. So to adjust the weights of the functions of the neural networks, there are lots of history about that, and lots of different kinds of networks introduced to change the weights and training the network. Two of the networks and algorithms to train the neural networks and adjusting the weights are Adaline and Perceptron. Actually, they are two classical history of neural networks. So we will review it very quickly in the next session. They are kind of history of neural networks, and we don't want to go into detail for each of them, but they are relatively simple. We will see that in the next session. So we will talk about adjusting weights of the neural networks in the next session. So hope to see you in the next session. Bye.